Hello students, good evening to all. So in previous classes we have discussed about Gauss law and its application to find Coulomb's law from Gauss law. Okay, but some of you have asked me, sir, what is a Gaussian surface? Okay, and what is solid angle? Okay, so when we use generally Gauss theorem, mainly we use solid angle concept. Okay, and when we divide angle, mainly we divide angle into two categories. One is called plane angle and another one is called solid angle. Okay, and plane angle, solid angle, both are, suppose one I consider plane angle and another one is, that is, solid angle. Okay, so generally plane angle is denoted by theta. Okay, and its unit is radian. Okay, but solid angle we generally represent as omega. Okay, and its unit is steradian. Okay, plane angle generally makes by any arc when we consider a circle. Okay, or when we consider two line, then intersection of two line will create that angle, and that angle is called plane angle. Or simply, when we consider a circle, then in such case, when we move on the perimeter of the circle by a small arc, okay, then we can say plane angle is an angle that makes a arc at the center of the circle. Okay, a plane angle is always made by a arc at the center of a circle. Okay, or simply it is made by cross section of two planes or two lines. Okay, that is called a plane angle, and oftenly we measure it in radian unit. Okay, but solid angle, okay, solid angle when we consider a surface. Okay, or we can say when we consider a volume element, then there is a idea of solid angle arises. Okay, so how can we imagine a solid angle? Okay, plane angle, it is easy to mark out what is plane angle, because we say that is intersection of two planes, intersection of two lines, or simply a arc made at the center of the circle. Okay, solid angle means it is a angle made by a surface. Okay, it is an angle made by a surface, okay, at the center of a sphere. Center of a sphere. Generally, I take a sphere in order to understand you better. Okay, so what we say, what we definition says, it is the angle made by a surface, okay, at the center of the sphere. That is called a solid angle. How can we imagine it? Suppose I consider a sphere. Okay, imagine a football sphere, solid sphere. Okay, and on that solid sphere, okay, on the surface of the solid sphere, just make a circle in your pencil or chalk. Okay, if we made a circle on the surface of a solid sphere and focus to the center of the sphere. Okay, if we made a circle on the surface of the solid sphere and if we make focus to the center of the sphere, and if we put out a region, okay, if you put out a region from this marked surface, then the region will be like, suppose I mark here a circle on the surface of the sphere. Okay, then what will I do? Okay, from that mark I will focus to the center. Okay, I will focus to the center region. Okay, center of the sphere, and pull out that region. Okay, how that region shows? Like this. Okay, that region is looks like this. Okay, if we mark a circle on the surface of a solid sphere, and from that circle focusing towards the center of the sphere, pull out a region. Okay, and that region is look like this. Okay, this is simply a surface. Okay, this region is a surface. Okay, and it will be like your cone ice cream. Okay, you have only eat in different mela or different shows. Okay, a cone ice cream. Okay, a cone ice cream like portion will pull out from that solid sphere. Okay, and in the cone the upper surface is that marked surface that you mark on the solid sphere. Okay, and that surface makes an angle. That surface makes an angle at the center of the sphere. Okay, and that angle is called solid angle. Okay, simply we can take cone ice cream, imagination to cone ice cream. Okay, so that angle is called a solid angle. Okay, and when we cover by marking all the region of the sphere. Okay, so if we mark all the region of the sphere, then we can make the total solid angle. Okay, so I generally here say two standard definition in order to determine the solid angle. Okay, so generally solid angle, this one is a small solid angle, that's why we represent as d omega. Okay, because it is made by a small surface ds, and when I cover the total surface, then the solid angle will be omega. Okay, so how can one find out a solid angle? Okay, so generally a solid angle is defined as like d omega equal to r cap dot ds vector divided by r square. Okay, it is a dot product ratio of unit vector. Unit vector means that is the unit radius. Okay, that is the unit radius of the surface. Okay, r cap dot ds divided by r square, that is one definition of solid angle. Okay, so here that we can otherwise say that is r vector dot ds vector divided by r cube. Okay, so from this relation you may find out the solid angle, or simply we can say here ds cos theta divided by r square. ds cos theta divided by r square. Okay, this is the one standard definition of the solid angle, from which we can easily prove what is the value of solid angle, because when we take omega, generally omega, that is integration of d omega. Okay, and when we consider the surface vector, and the unit vector, okay, r cap and here that is the ds vector are in same direction, then theta equals to 0. Okay, so that will be ds divided by r square, because cos 0 equals to 1. So ds by r square, if you take 1 by r square outside, so integration ds, s is the surface. Okay, so in case of a sphere, the total surface area. Okay, so s is the total surface area. What is the formula for surface area of a sphere? Okay, so that will be 4 pi r square. Okay, so if you cancel r square, then omega will be 4 pi. So that is called a solid angle. Okay, another way of determining the solid angle is this one is a sphere. Okay, so another definition of the solid angle is omega equal to 2 pi into 1 minus cos theta. Okay, omega equal to 2 pi into 1 minus cos theta. If we consider half angle, okay, that is called half angle. This region is called half angle of the sphere. Okay, if I consider a half angle, then in such case half angle theta equals to pi by 2. Okay, for half angle theta equal to pi by 2 and region is a hemisphere. Okay, so that region it forms, that is called a hemisphere. Okay, for hemisphere theta, that is called a half angle is equal to pi by 2, this region, that is a hemisphere. Okay, theta equals to pi by 2 and the region is called a hemisphere. So in such case solid angle equals to 2 pi into 1 minus cos pi by 2 1 minus cos pi by 2, so that's equals to 2 pi. Okay, so that means we can say the solid angle for hemisphere, okay, for hemisphere solid angle is 2 pi. Okay, if I consider a full sphere, full angle, okay, for full angle theta equals to pi. Okay, for full angle, that is the total sphere. Okay, total sphere is called the full angle. For full angle theta equals to pi, and when theta equals to pi, then omega equals to, that is called total sphere. Okay, so omega equal to 2 pi into 1 minus cos pi. Okay, so that equals to 1 minus, so 1 plus 1, so that omega equals to 4 pi. That is also one of the form of solid angle, 2 pi into 1 minus cos theta. Okay, half angle theta equal to pi by 2, half angle means it is a hemisphere, that will be 2 pi, and for the full sphere or full angle theta equal to pi, so that is omega equal to full pi. So generally the angle of solid angle for a sphere will be 4 pi. Okay, another thing, what is a Gaussian surface? What is a Gaussian surface? Okay, what is a Gaussian surface? Okay, so generally Gaussian surface is a hypothetical surface, or simply we can say it is a imaginary surface, okay, which is used to determine the electric field. Okay, so generally Gaussian surface, we can say any hypothetical surface or simply an imaginary surface, any hypothetical surface enclosing a charge is called Gaussian surface of that charge. Surface of that charge. Okay, simply we can say Gaussian surface is a imaginary surface that enclose the charge of any body of any surface. Okay, so generally we cleverly choose that surface. Okay, we cleverly choose that surface in order to find the electric field. Okay, so it is a hypothetical surface enclosing a charge, that is called Gaussian surface of that charge, or simply we choose cleverly that surface that enclose the charge, and it is used, or it helps us to find the expression for electric field by using Gauss law. Okay, so what type of Gaussian surface does the charges region takes? If I consider a point charge, okay, if I consider a point charge, okay, for a point charge the Gaussian surface is spherical. Okay, a Gaussian surface is a spherical surface. Okay, what is a Gaussian surface for line charge? Okay, if I consider a line charge, okay, that is the linear charge. For linear charge, the Gaussian surface is cylindrical. Okay, if I consider a plane sheet, then the Gaussian surface is also, we take a cylindrical nature. For a plane sheet, the Gaussian surface that we also take is a cylindrical in form. Okay, so these are the different types of Gaussian surface. Okay, another important thing is that how can we find the surface vector? What is surface vector and how can we find? Okay, so generally surface vector, these are you have already studied in your first year classes in kinematics part. Okay, so what is your surface vector? Okay, a surface vector is generally represent, or simply we represent surface vector as ds vector for any surface. If I consider this is a surface, okay, having surface area S, okay, and if I take a small surface region ds, then in such case surface vector is equal to ds n cap. Okay, that n cap is the unit normal to that surface, and generally that n cap is called a surface vector. Okay, and n cap direction is always outward from that surface. Okay, that is n cap. N cap surface vector is always outward from that surface. Okay, so ds vector equal to dx n cap. Ds is the magnitude, n cap is the, that is the direction, unit vector. Okay, and for any surface the unit vector is always away from that surface and it is perpendicular to that region. Okay, important is that it is perpendicular to that region. It is away from the surface. Okay, that means radially outward. Okay, and it is always perpendicular to the chosen surface. Okay, so that is called a surface vector. Now question is, if I say it is perpendicular, so how can one draw a surface vector for a curved region? Okay, so if I consider a curved region like this, if I consider a curved region, how can we draw the unit normal? Okay, we say surface vector is unit normal to any surface and its direction is always away from that surface. Okay, so what we can, how we can draw a surface vector for the curved region? Okay, so first come to find out the surface vector for any plane region. Okay, so if I consider a cubical box, so in case of cubical box, we say there are 6 faces. Okay, there are 6 faces, so it is easy to find out the surface vector because we say the surface vector is radially outward and it is perpendicular to that surface. Okay, like this one. Okay, this one is my surface, and if I take a surface vector like this and its region is vectorically outward and perpendicular to that region. Okay, so for Q we can say that is the surface vector. For this surface, that is the direction of surface vector. For this surface, this one is the surface vector. For this region, okay, this one is surface vector. For this region, this one is surface vector, and it is radially outward. For this region, okay, this one is the lower region, so vectorically outward direction, it perpendicular to the surface. Okay, for this region we may this was like this one. Okay, so this will be like this. Okay, so I draw here. Okay, for the below region, this region, the vector will be like this. So it is easy to find the surface vector, and it is easy to represent a surface vector for a cubical region. But if I consider to determine the surface vector in case of a curved region, this one, okay, how can one draw surface vector on a curve region. Okay, for the curve region, when we find any curve region, just put a small square on that region. Okay, when you find any curve region, just put a small square on that curve region. As we know, smallest distance between 2 points is always a straight line. Okay, smallest distance any 2 points is always a straight line. So that's why when we draw a small square on the surface, that will give a figure of square, because this there becomes straight line. Okay, now draw perpendicular to that square. Okay, now draw perpendicular to that square, and that will represent surface vector for that curve region. Okay, so when we find surface vector for any curve region at any point, then when you take a small square on that point, because that if the smallest distance between any 2 points is a straight line. Okay, and draw a unit normal to that square. Okay, and its direction is normally outward, and that will represent the surface vector to that curved surface. Suppose here I want to take, suppose this one is my sphere. Suppose here I want to measure a surface vector. Okay, so simply I mark here a small square. Okay, and draw a perpendicular to that square. So that will indicate the surface vector for this curve region. For this curve region, this is the surface vector. Okay, so that is the way to find out the surface vector. Understand? So now let us come to our chapter, come to our topic that we have discussing, that is applications of Gauss law. Okay, already we have discussed about the first application to derive Coulomb's law by using Gauss law. Okay, now come to the second application of Gauss law. Second application of Gauss law, that means electric field due to linear charge distribution. Okay, second application of Gauss law, that is linear charge distribution. Okay, or simply we can say wire or line. Okay, wire application or line application. Okay, linear charge distribution. Let's have a look. Suppose I consider this one is a wire of length L, and that wire contains q amount of charge which is uniformly distributed over that surface. Uniformly distributed over that surface. Okay, another important thing, how can we one find for a cylinder? Okay, this one is cylinder. Okay, for cylinder there are three surfaces. This one is plane surface, this one is also a plane surface, and this one is a curved surface. Okay, for the curved surface you may draw a small square and unit normal, that is ds vector, and here we can simply, this is plane, so another ds vector, and this one. So there are generally three surfaces: lower plane surface, upper plane surface, and that curved surface. Okay, cylinder has three different surfaces. Okay, so come to this region. So this one is a line or wire of length L that contains charge Q, and that charge Q is uniformly distributed on that wire having linear charge density lambda. Okay, so lambda is the linear charge density, so the lambda equals to Q by L. So that's why you can say Q equals to lambda L. Let us take equation 1. Okay, so in order to determine the electric field at any point P, okay, suppose we want to measure electric field at any point P from that wire, and point P is at a distance of r from the wire. Okay. So, in order to determine the electric field because of the linear charge distribution by using Gauss law, okay, we have to imagine a Gaussian surface. Okay. And for a linear charge, the Gaussian surface is simply a cylindrical surface. So, let us imagine a Gaussian cylindrical surface of radius r. Okay, that means it has to pass through the point of observation P, okay, of radius r and length L. Okay, so that Gaussian surface has radius r and length L, and it pass through the point of observation P. Okay. So, now in order to determine the total electric field at point P, simply when we draw a Gaussian surface, we find for that Gaussian surface there will be three regions, that is lower circular region, upper circular region, and this one is the curve region. Okay, this curve region. Okay. So, since it is a positive conductor or positive wire, then my electric field is always outward, like this, from that region uniformly outward direction. Okay, from that region it will be like this, all direction, so that a cylinder encloses all the electric field, but it is a infinitely small wire. Okay, so linear charge is infinitely small wire, so that's why upper region is very small. Okay, so electric field is always moving from that wire. Okay, so that's why you can say this will be, suppose there is a small surface of surface area ds, and this will be the direction of electric field. Okay, this one is positive, so electric field is always away from the positive wire, so this will be the direction of electric field, and this is also direction of the surface vector for that small region. Okay, from this point this will be the direction of electric field, and for this surface the surface vector is here ds vector, and for this lower circle this will be the direction of electric field, and surface vector is downward direction. So, here the angle theta equals to 90 degree, upper angle theta equals to 90 degree, and this region theta equals to 0 degree. E and ds are in same direction. Suppose I divide it into three regions, region 1, okay, region 2, and that curve region 3. Three different regions, region 1 upper circular region, region 2 lower circular region, region 3 that is curve region. Okay. So, the wire has length L and it contains charge Q that is uniformly distributed over that wire. So, lambda is the linear charge density, lambda equal to QL. So, Q equals Q by L. So, Q equal to lambda L. Okay. So, if we use Gauss theorem in order to find out the electric field, then we find for this Gaussian surface the total charge will be Q, because the line is totally covered by the Gaussian surface. So, inside the Gaussian surface the total charge enclosed is Q. So, we can use here the Gauss law, that is according to Gauss law for the Gaussian cylindrical surface, closed integration S total flux, closed integration S E dot ds equal to Q by epsilon 0, because that Gaussian surface contains total Q amount of charge. Okay, and we divide the total surface or total surface region into three different regions. Okay, total surface of a cylindrical region into three different region: upper circular, lower circular, middle curve region. Okay, so my closed integration S is now integration over region 1 E dot ds plus integration over region 2 E dot ds plus integration over region 3 E dot ds equal to Q by epsilon naught. Okay. Now, for region 1 the angle is theta equals to 90. Okay, so simply convert integration over region 1 e ds cos 90 plus for region 2 that will be e ds cos 90, and for region 3, okay, e ds cos 0 equal to q by epsilon naught. Okay, understand? Now cos 90, what is the value of cos 90? Cos 90 will be 0. So if cos 90 is 0, this one is 0 plus this one is also 0 plus e ds cos 0, that will be 1. So integration over region 3 e ds equal to q by epsilon 0. Okay, my region 3 is curve region. Okay, so what is the surface area? So take E outside, so integration over region 3 ds equal to q by epsilon 0. Okay, so what is the area of the curve region? What is the area formula for area of the curve region of a cylinder? Okay, here we consider cylinder has length L, radius R. So what is the curve area of the curve region? 2 pi RL. Okay, so that will be 2 pi RL equals to q divided by epsilon 0. Take it small l. Okay, so that implies 2. So we have, what is the M to find? That is electric field. Okay, so E equals to q divided by 2 pi R L into epsilon 0. Okay, so substitute the value of q equals to what is lambda L. Okay, so E equals to lambda L divided by 2 pi R L epsilon naught. Okay, so E will be lambda by 2 pi R L, sorry, lambda by 2 pi epsilon naught R. So that will be the expression for electric field due to infinitely linear charge distribution, infinitely thin wire. Okay, so E equals to lambda by 2 pi epsilon naught R. So here we can say E proportional to 1 by R. That means when we increase the point of observation distance, then electric field gradually decreases. Okay, so this is about linear charge distribution. Okay, so I think all of you should be clear about the linear charge distribution. Okay, so next we discuss about the planar charge distribution. Okay, thank you.